I want to make sure we do the quiz today in class. So I want to make sure I start on time. Okay, it's 9:30. I'm going to start. Okay, so everyone with me? Good morning, everyone. Okay, so I am looking first at last Tuesday's module where we found the moments in a 2D problem using the right-hand rule. And I'm just going to open up the overview because remember the overview and it has the summary of what we learned. And I'm going to skip all this stuff here, but down here, when we're trying to find the moment about a point for a 2D problem using right-hand rule, the first thing we do is we find the force. The next step, so we're looking at where the force is. Next step, is the perpendicular distance given, meaning is the distance between the force, perpendicular force, to the point I'm trying to find the moment about given. And maybe I should, let me write that better. Is the perpendicular distance shown, meaning is the distance perpendicular from the force, or rather perpendicular to the force, no, I'm going to say from the force to the point I am trying to find my moment about given. So we look at where the force is. Do you know the perpendicular distance between the force and the point in question? And if not, then you break the force into components using the two-step process and make sure you do the plus or minus visual and the magnitude check. Then you calculate the magnitude of the moment by taking the absolute value of the force times the absolute value of the perpendicular distance. And then, and this is to find the moment magnitude. And then you use the right-hand rule to find the direction of the moment. And then if it winds up that there are more than one forces, or you have the X and Y force, then certainly the moment about the point is the sum total of all the moments. So I'm going to just save that. I'm going to move us up, photos up, and save. Okay, so everyone, if you have a two-dimensional problem and you're trying to find the moment by the right-hand rule, you look at where the force is. Then you check to see if you know the perpendicular distance between that force and the point you're finding the moment about. And if you do, you just go ahead and use the right-hand rule. If you don't, you break up the force into components, X and Y, and then use the right-hand rule using those perpendicular distances. Does anybody have any questions about that? I'm going to just make a comment on the lab you did on Friday was pretty ingenious, but it was a little intense, but it was amazing. It was awesome. And it was teaching you at another level. Can everybody see my picture? So we had a circle, and the first, he gave you angles written on all these lines. And the first angle that he gave you was to find the point where the force is. And then the next angle, I could always talk to you individually if you have questions. The next angle was the angle of the direction of the force. But what I wanted to concentrate on is in this problem, what he was having you realize is that instead of breaking, you didn't have the perpendicular distance between, here's, let's say, F1. You didn't have the perpendicular distance between F1 and the point you were finding the moment about. But instead of breaking it up into X and Y, if you broke it up into X and Y, you wouldn't have had the perpendicular distance to the center either. So what he was having you do is break this force into a component that is right through the center and a component that's tangent to the circle. Because this force, does this component of F1 that goes through the center create a moment about 1? Amani?
I'm all good.
No, okay, sorry. So the answer is no. So
Oh,
instead of breaking the force into X and Y, he broke the force into a component of the force that goes through the center, which creates no moment about this point. And then he broke it, the other component he broke was tangent to the circle, and then you have that perpendicular distance because it's the radius. So this is really interesting. So one, in the lecture, we first saw problems where we had the perpendicular distance given. So we just took the magnitude of the force, magnitude of the distance, and did right-hand rule. Then we had problems where we didn't get the perpendicular distance and we broke it into X and Y because the distances that were given in X and Y directions. The problem he did in the lab is the distance that you were given was the radius of this circle. So what he did is he took this force and broke it into components, not the X and Y, but he broke it into components that would help him solve the moment about point O. This force goes right through O, so it doesn't create a moment. And this one has the perpendicular distance. So now hopefully you might understand that problem in lab a little deeper and go back to it because you could totally do it. Okay, I'm going to go back to sharing my screen again now. And I'm going to go back to modules. And the next thing we did, so last Tuesday, we did a 2D problem with using right-hand rule. And then on Thursday, I'll just go over the overview again. We did both 2 and 3D problems, solving for moments vectorially. And how did we do it? R cross F. We got the R vector, we got the F vector, we crossed them. Okay? And notice, everybody look up here. If my force goes from B to C and my moment I'm trying to find is about A, R goes from A to the tail of the force. Although I taught it that way, I want to add to you, and you'll see on one of my solutions for the homework, you could actually, your R vector doesn't, yes, your R vector could go from the point you're finding the moment about to the tail of the force, but your R vector actually could go from the tail, from the point I'm finding the moment about to any point on the force. So let me stop sharing the screen for a minute. So look at me, or rather, no, let's look at the picture.
What are you jacket over it? I think it's so fucking great.
Put yourself on mute, you guys. Victoria, put yourself on mute, kiddo. Okay, so everybody, on last Thursday, we found the moment about point C due to this force. And we went from C to A, right? R goes from the point I'm trying to find the moment about to the tail of the force. But actually, R can be drawn to any point along this force. So in this case, we don't have any dimensions, but here, this is RCB. And if I crossed RCA with force AB, let me write that down. I'll write it up here. RCA crossed with FAB is equal to RCB cross with FAB. And this is the moment about point O. These two values are exactly the same. And the reason why is when you have a cross product, here we have an R vector and an F vector. the moment, the vector that you get when you cross two vectors is a vector perpendicular to both of these. Whether you cross RCA with FAB or cross RCB with FAB, you're going to get the same value. The vector, the R vector is different. The A vector is the same, but you'll find that you'll get the same value for the moment. Okay, so that's a little tidbit. I always go to the tail.
Can you slide the paper up a little bit and maybe
Yeah.
focus the camera?
Yes.
Thanks.
I always go to the tail because for me, when I'm consistent, I make less errors. But
That's
you
good.
can go to the head. So what I want you to do when you do go through your homework and you check your solutions with mine, you'll notice there's one problem where I do both. I go to the tail, I do my R vector to the tail, and I do my R vector to the head, and I get the same value. Okay?
Joanne.
Okay. Yes, David?
Yeah, I was gonna say, I think it's problem 23 where that's particularly helpful. It's like it's a force vector that's going into the point you're talking about. And so rather
Right.
than having to move the tail, you can just do it like that.
Great, and that might be the one I did, but I'd have to go back and let me just look quickly.
I just remember having a really hard time with that one because trying to move the tail in 3D is
And it was
funky.
23,
Yeah.
3D moments.
Joanne, does it matter if you write the forces FAB or FBA?
I can't find which one I did it, but I did it for one of them.
Don't worry about it.
Okay, Jordan, what did you say?
Does it matter if you write the forces as FAB or FBA?
Yes, it does. Because now you're flipping the direction of the force. Think about it. In this case, I'm finding the moment about point C, it's going to go this way, right? Clockwise. If the force is going in the other direction, the moment's going to be counterclockwise, right? Does that make sense, Jordan?
Yeah, so RCB can be crossed with FAB and you just,
RCA can be crossed with FAB and RCA can be crossed with FAB. Both of these are the same. The force is always going in the same direction. The
Okay,
force,
thank
the direction vector is just going to a different point on here. Okay, now, I would like to move on if possible. Jason, quick question.
Well, I'm sort of coming to the realization that it matters where the force vector is. And I think that's something that, at least in mathematics, we've been used to being able to move vectors around and have them be equivalent. But you can't do that here. Obviously, if you put its tail at the point, there would be no moment. And so it's absolutely critical where the vector is. That's kind of unusual.
Yes, you could move the force anywhere along the line of action of the force, but you can't move it anywhere else. Think of this physically, right? Physically, where the force is will control what the moment is. You have a wrench, right? If you put the force in the middle of the wrench, you're not going to get as much leverage as if you put your force at the end of the wrench. You'll get more leverage.
Right.
And what do I mean by more leverage? I'm going to be able to get a larger moment. So you can't move forces other positions because that's it's different, but you can move it along the line of action. So think of it in a physical sense. Okay, so I'm going to move on now. Okay, and now okay, I'm going to Angel next. Or rather, I want you to think about this for a minute, everyone. Okay, our topic for today is finding moment about a line. Does everybody see that? That's our topic for today. Up till now, we found moments about points, right? Would everybody agree? We found moments about points.
Yes.
When you find a moment about an x-axis though, right? Let's look at what we did already. On Thursday, we solved for what RCA is, and this is the value for RCA. Then we solved for the components of the force AB. And we crossed these two guys, right, to get our moment about point C. And there was an X, Y, and Z component. Even though we were solving for the moment about a point, didn't we really find moments about a line in a way? We found the moment along the x-axis through C. We found the moment, the y-axis through C, and we found the moment along the z-axis through C. Does everybody agree with that? We found a negative 180 in the eye. Wasn't spinning this way, it was spinning that way. But in a way, we kind of found a moment about a line already because an axis is a line. It has a unit vector. But now we're going to move in finding a moment about any line. So the line that I want to find the moment about, I have it written right here. Can everybody see this right here? I want to find the moment about line CD. I already found the moment about point C, and I know the X, Y, and Z components, but I want to find the moment about line CD. So could you guys think about this? And I had a discussion with a few people before in office hours. Whenever I know you are not confused about forces. You have a force going in a direction, and you have no problem finding the components of that force because you've been doing it since your maybe 8th grade. You've been finding components of forces. And we all think in X, Y, and Z, right? And if you look at a building, maybe one that's kind of boring, a boring building like the UN, it's totally rectangular. All the walls are in the X, Y, or Z plane. All the lines of the corners of the buildings are in the X, Y, or Z. But if you look at a cool bridge like that one in Dublin we saw, we're not always looking at lines that are in X, Y, or Z. But we spatially have always been thinking about X, Y, or Z. So what I'd like you to do is you are totally comfortable finding components of forces. And now what we're really trying to do is find the component of this moment along this line. You're comfortable with forces. The fact that this vector moment is spinning makes you a little bit uncomfortable. But if there was a force, now Angel, I'm going to ask you now. Angel, you're here? Yeah. If you had a force at point C and you wanted to find the component of the force at point C that's along the direction of CD, what would you do?
Would take the dot product, right?
Great. So if you had a force, if you wanted to find a force along CD and you had the force of C, you would dot it with the unit vector of CD. Is everybody comfortable with that? If you had a force at point C and you wanted to find the component of that force along CD, you would dot it with the unit vector. Thumbs up with everybody? Okay. Well, we're not dealing with forces. We're dealing with moments. So Bon, if I wanted to find the moment about CD, I want to find the component of the moment about C in the line of CD. How do you think I find it?
I would think you take the cross product.
Okay, I'm trying to find, it's the same exact thing. I know that when we deal with moments, it kind of blows you guys out the water. Think of moment as a vector. It's just like a force. I want to find the component of this moment that has a certain spin, and I want to find its spin alongside CD. What do? The moment about CD is equal to the moment about C.
Maybe the dot product of the, I was I was gonna say the direction of it, but I'm not sure that's right.
It's the unit vector. It's exactly the same. Can you see what I wrote under here? If you wanted to find force, the component of the F force in the direction of CD, you would dot the force of C with line C, with the unit vector CD. Same thing. A moment is a vector, just like a force. It's just instead of a pull or a push, it's a spin. But the component, if I want to find the component of the spin, the moment about C, about line CD, I do the same thing. So let's get the unit vector of CD. Colin. Colin, you here? Yeah. Colin, going from C to D, how would I calculate the unit vector? And notice, remember whenever we do with deal with 3D, we have to make sure we see where their axes are. Here's the X, here's the Y, and here's the Z. So what direction is it going from C to D? What's the direction in the X?
Negative.
What?
Negative 100.
Yeah, negative 100I. And then in the Y?
0.
0. I won't even write it. And how about the Z?
Positive 120.
Right, positive 100. Now, is this the unit vector?
If
No.
you're writing, we can't.
Oh, sorry.
Can't see it, sorry. No, you're right. This is not the unit vector, right? This is just the distance vector. So what do I have to do? I have to divide it by what, Colin?
You have to, so you square each one,
Right,
and then you add them, and then you find the square root of that.
right. Okay, so it comes out to be, let me just look it up. Negative 0.6400I plus 0.7680K. Are there any units, Colin?
No.
No, because it's a unit vector.
Hey, Joanne.
Yes, Jack.
When you divide it by where did the 200 come from?
Oh, I'm sorry.
That'd be 120.
Yeah, thank you. 120. Thank you. Hey, I want to write something. ECD is equal to my R vector CD over the absolute value of the R vector. Daniel C. Is this correct?
Let's see, RC, so we have it divided by the magnitude. I would say it is, I want to say it is because like we have a, yeah, I would say it's correct. Yeah.
It is. Isn't this negative 100I plus 120K, isn't that the distance going from C to D?
It is, yes.
So it's the R vector. And then squaring those guys
Give us a magnitude.
gives us the magnitude. This is correct. This is very important because at least 5 of you, or in the past, maybe not this time, but in the past, at least 5 people in statics, when I asked for the unit vector, they gave me the R vector. And if I asked for the R vector, they gave me the unit vector. So remember that there is a difference, and I know you know there's a difference. There's a difference between the unit vector and the R vector, but sometimes just check your work because by accident, you write R instead of E sometimes, or E instead of R. Okay, so now I need to, who's talking?
Maria.
Maria, yeah.
So to find the moment about CD, it's the moment of C times the unit vector.
Dotted.
Could it be the moment about D times or dotted with the unit vector, or would that be something different?
No, it wouldn't be because let's not go into that, okay? And I want to show you another route that we're going to use. So let's wait to the end to talk about that, okay?
Okay, because I'm just confused about how you know which moment to pick.
Because I'm trying to find it about CD, and the definition is in order to find the moment about CD, going from C to D, I have to find the moment about the tail.
Okay.
It's just like if it was a force.
Okay.
Because if we did D, then we would be looking at the component of the D moment. And we're trying to find the component of the moment about C that goes in CD.
Okay.
Okay? Okay, so. Okay, so we said that the moment about CD is equal to the moment about C dotted with ECD. And just to write it over, the moment about C was equal to negative 180I plus 36J minus 150K Newton meter. And now we found out that the unit vector is equal to negative 0.6400I plus 0.7680K. Okay, so how do we dot them? MCD is equal to MC dotted with ECD.
Joanne,
What do we
I'm
do?
sorry. Where did the 18036 one come from? That's from a
It
previous
came
problem,
from-
right?
It was the problem we did before. So this problem, we had already calculated what the moment was about C on Thursday.
Okay, so we're talking about the moment caused by AB
Correct.
around the whole line CD.
Yeah. So let me just
Okay.
start from the beginning again.
Okay.
We have a force AC, and the force AC from last week. What I'm trying to do is do the same problems each class so that you could see the different ways to do the solutions for the same problem, so you could compare them together. So on Thursday, we did moment about point C due to this force. So we calculated what FAB was, and we calculated what RCA was, and we used the cross product, and we found out what MC was, negative 180I plus 36J minus 150K. So this is what we calculated on Thursday.
Okay, and that's just about point C.
Correct.
All right.
Just about point C. That's why it's really important to use subscripts. So this is the moment about point C due to F going from A to B.
So maybe the explanation for Maria's question, because I have the same question, is that we have information about point C, so we want to start this thought process from point C out to point D. Is that the reason?
Yes, yes, yeah. And because the problem had already asked, the problem on Thursday asked you for the moment about C, and now the problem today is asking you to find the moment about CD. So
Okay.
what we're doing is we're finding the component of the moment about C in the direction of CD. Good?
Yeah, thank you.
Okay, great. Okay, so how do we, we're up to, David C., did you answer already on a previous question?
Yeah, but what was the question you're gonna
Not
ask?
David, Daniel. So Daniel Hall, is Daniel H. here? Daniel I.
Yes.
Oh,
Just need
Daniel
Daniel
Hall, you're
H.
here?
Yeah.
Okay, so how do I get the dot product of two vectors? What do I do?
Uh,
Do you want to pass? Okay, Daniel I.
Yes, hi.
Yeah, I want to find the dot product. How do I find the dot product of these two vectors?
Multiply the same, the i's together, the j's, and the k's.
Yep.
How do you describe that? Is that how you describe that?
I would say multiply the x components and then add the multiplication of the y component.
Okay.
Okay, so there's no y, and then it's negative 150 times 0.768. And it's a dot product, so should I get a vector or a scalar?
Kaylee.
I'm going to get a scalar. And the reason why is I'm trying to find the component of the force of the moment all on that line. So I'm finding the component along this line. So the moment about CD, what does it turn out to be? Negative 180 times negative. I got 0. Somebody else get 0?
Ooh, I think I know why.
You're always a step ahead of us, Jason.
Yeah, I got 0 too.
I got negative 230.
230?
Negative 230.
Is it not negative 0.23?
It's negative 230.4.
Okay, so check your math because it's
Yeah.
0.
I
Okay.
got 0 also.
Okay, Daniel, don't spend time now checking your math. Let's just deal with the statics.
Oh, I got
Okay.
0.
Okay, great. All right, now everybody take a look at this picture. Let's zoom in. So let's think about this. We have a force going here, right? And we're trying to find the moment about this line due to that force. So there are two possible options. Okay, so we're on David L. There are two possible reasons that this force creates no moment about that line. And what is one possible reason?
I think it's because they are on the same plane. So if you've got your A, B spinning, it's hard to describe, towards you, like out of the paper like that, it's not going around the axis that CD causes. It's not going around the CD axis at all. It's going along it.
And you guys, David has do you mind I say it? Bachelor's degree in math.
Oh, sure, go ahead.
Actually, what?
I said, that's fine. You can out me.
Okay. And he actually said both answers in one answer. The answer is that they're in the same plane. So if I put a piece of paper here, they're in the same plane. But let's back up. Let's think about, and we'll get back to the same plane. That is the main answer. But the other two answers I was looking for are the only way two things could be in the same plane. So David LR, tell me a relationship between this force and this line in order for no moment to be created about the line.
Them being parallel?
Great, parallel. If a force and a line are parallel, this force cannot create a spin around this line. Or do you get it? If this force is parallel to this line, this force cannot create a spin around this line. That's one scenario. Edgar, what's another scenario? Can you think of how could this force not create a moment about that line? Take a look at the picture. I'm kind of giving it away a little.
Well, so you're trying to show that they intersect at some point?
Yes, they intersect. You might want to put your volume up. Yes, if they intersect, if a force and a line intersect, the force cannot create a moment about the line, right? So,
Because it means that they're on the same plane.
right, which that's where I'm getting now. So in order for a force to create no moment about a line, the force is either parallel to the line or the force is perpendicular to the line. And if either of these case either of these two cases exist, the force is on same plane as the line.
But in that previous example, they're not perpendicular to each other. They just intersect, right?
Oh, I'm sorry. Sorry. Thank you.
Yeah, perpendicular would be a lot of force.
It would depend, right? If they're, yeah. Okay, yeah, you're right. I made a mistake, okay? It's intersect. Okay? If it's perpendicular, if they're perpendicular but they intersect, then you can't. But if they're perpendicular and they're not on the same plane, then they do create a moment.
Wait,
Hang on.
we're talking about creating a moment around an axis, around a line, around an axis.
Correct.
And in that case, if the force intersects that line, that axis at any point, you're not getting there won't be any moment around the axis, no matter
Correct.
whether it's perpendicular or not.
Right, if there's an intersection. So here's a line. My green Tinker Toys is a line. Okay? And I have it sitting on a plane. And here is my force. See the arrow? The force, two lines, if they're on the same plane, they're either parallel and never meet, or they at some point must intersect. So on a plane, if I have two vectors on a plane, either they intersect at some point, maybe they intersect off the page, but they intersect on the line, or they're parallel. Now that's the math theorem. Now let's look at statics. If I have a force that intersects a line, where am I? Elizabeth, are you here? Eric.
Hi.
You're here? Okay, great.
Yeah.
So Eric, if a force intersects a line, can it create a spin around that line? Or is it just going to push the line?
It's just going to push the line.
Right. Remember, there are two different types of motion. There's linear, which you could call translational, or there's rotational. If a force hits a line, it cannot create a spin around that line. So there's no moment about the line. If a force is parallel to a line, it cannot create a spin about this line either. The only time a force can create a spin around a line is if they're not in the same plane. If they are in the same plane, they either intersect and are parallel, and the force cannot create a moment about the line. But if they're in different planes, this force can create a spin around that line. So for those of you that are still, need me to say it again, I'm going to have you watch the video. Watch this taping. So I want to go back. We wanted to calculate the moment about line CD. And the way we did that is we found the moment about the tail of the force, the tail of the moment rather, and we dotted it with the unit vector in that line. So what David had asked earlier is, well, where did we get that MC from? Well, MC was RCA cross FAB. So in order to find a moment about a line, this is option 1, because I'm going to introduce you to option 2, which is quicker. Option 1, the moment about a line is equal to the moment of the tail of that moment, the moment at the point of the tail, dotted with the unit vector of that line. And I found that moment by doing R cross F first. So first I did R cross F, I, J, K, R, X, R, Y, R, Z, F, X, F, Y, F, Z. And then I dotted it with the unit vector. That's option 1. I want to show you option 2, which is a lot quicker. Option 2, we're going to go straight away and find the moment about CD without finding the moment about the tail of the force first. This is equal to EX, EY, Z, RX, RY, RZ, FX, FY, FZ. I'll wait until you write that, and then I'm going to go back a
Those
little.
are equivalent, right?
They're equivalent.
MC is that thing you wrote out, RCA, FAB. That's the same term, right?
They're exactly the same.
Okay.
But what we did here is we did an intermediate step of solving for the moment about C first. If I don't ask you what the moment is about C, you could go ahead and just do the determinant.
Okay, thanks.
Hey, Joanne, can you move that up?
Yes. Okay, so I want to go backwards. The problem on Thursday asked for you to find what the moment was about point C. So we figured out what RCA was. We figured out the vector form of the force. We did R cross F. We found out what the moment was about C. And then in order to find the moment about CD, we dotted the moment we got on Thursday with the unit vector. Now, instead, let's just go straight ahead and not find the moment about C. So RCA is equal to negative 100I plus 250J plus 180K millimeters. FAB is 400I plus 500J minus 360K newtons, and ECD we found was negative 0.6400 I plus 0.7680 K, no units. So MCD is equal to, you put the E up here, 640, 0.768. You put the R in the next,
move it down.
Next row. 100, 250, 180, 400, 500, negative 360. And when you plug it into your calculator, you get it equal to 0 because of the point we talked about earlier.
So given that we're going to use calculators to do the matrix math,
yes,
I think those two options are the same. I think we're going to push this exact same buttons.
Yeah, well, here when you solve for MC, you have to put the I, J, and K in there, right? So you have to do it in a different way than you do here, because this is just the determinant.
That might just be a my method question. That's fine.
Okay. So what is the difference, Gerardo? What is the difference between option 1 and option 2? what extra step do we do in option 1 that we don't need to do in option 2? Gerardo here?
I like to pass.
Okay, Hyoji? You here?
Yes.
Okay, Hyoji, doing option 1 or option 2, what's something that I have to do in option 1 that I don't need to do in option 2? You want to pass?
Yes.
Isaac?
You're asking what's the difference? I'm actually not clear on the difference between option 1. Like Dave, I don't really see the difference.
Okay, all right. The difference is first you solve for, so let's just write so for option 1, we first, actually let me just show you in the overview, okay? The deal is that option 1, you have to solve for the moment about a point first. Where in option 2, you don't solve for the moment about the point at all. You go straight away and find the moment about the line. Okay, so let me stop showing this.
Joanne, are there
Yeah.
units for that moment? Are the units different?
Yeah, tell me, what do you think? What's the units?
Maybe Newton millimeters?
Yeah, Newton millimeter. You're right. I probably should have wrote 0 Newton millimeter, not just wrote 0. Thank you. Okay, I'm gonna share.
Can I ask a question?
Yeah.
Is the difference just like whether you ask us for the moment about point or not?
Yes.
Oh, so we're finding the same thing either way. It's just, do you want the moment about the point, or do you just care about the spin?
Right. It's the process.
But you.
Okay.
Question of which results you're asking for?
Wait, can we use the bicycle example that I've used a number of times? If you have a force and you want to know the moment, the torque that it's creating about a bar on the bicycle, you don't need to find first the moment that it creates about the point on the bicycle bar. You just need to find the moment about the whole bar. Just hang on a second and let me open this up. I'm sorry this is confusing. This shouldn't be confusing.
Okay. So
okay, wait.
It's a question of what are we looking for?
Okay, there are 2 methods to determine the moment about a line due to a force. Okay, so we have a force and we're trying to find the moment about a line. So let's just say in this example, you're trying to find a moment about line AB and the force is on CD. Method 1, option 1 is determine the unit vector of the line, determine the force, and determine the R vector at the tail of the line. Notice step 1 and step 2 is the same exact thing. If we're trying to find a moment about a line, we need to know the unit vector of that line, we need to know what the force vector is, and we need to know what the R vector is, whether we do method 1 or method 2. In method 1, I'm having you stop, do an intermediate step, and calculate the moment about the tail of the line. Remember, the line is from A to B. So I first have you calculate the moment about the line, and then I have you dot the moment about that line at the tail to the unit vector of the line. So in the first option, I'm finding the moment about the tail of the line, and then I dot it with the unit vector of the line. In method 2, I don't calculate the moment about the point at all. I'm only finding the moment about the line, and I do it with a determinant with a 3x3 matrix, with E as the first row. So if you have a problem where they're asking you for a moment about a line, you don't need to calculate the moment about the point first. You could go straight away and just calculate the moment about the line.
Oh, okay, so literally the difference is just, do we care about the moment about the point or not?
That's right.
Other than that, they're the same.
Right.
Oh, okay, that's what I was missing.
I think if you showed it like written out, you would, you know what I mean? Like the two different ways, it's like pretty clear that the second way is going to save you a step in time.
Yeah. I'm going to go get some water and just give you 5 minutes to talk about it among yourselves. I'll be right back.
I guess it would save you time if you're writing out all of your matrix math, but I don't recommend doing that. I've been using tools to do the matrix math.
What are you using?
A calculator, a TA89.
So you say matrix math, but it's a determinant. Oh, actually, yeah. Oh no, this is better because the outcome is a scalar, which you can actually use the determinant function of a matrix solving calculator to find this, rather than it being a vector where we had to do 3 different determinants. Is that what you're going to do?
I think I maybe I am overthinking it, but I have Isaac's question. I think it's the same method. It's just like doing some. It's not stopping in the middle. I don't know.
Yeah, it would seem my understanding of what she said is that the second method is the quickest, and so it's just you use that one if you just want the moment about the axis, about the line. The first method allows you to find the moment about the point along the way.
If you care.
If you care, like if she asks, and if she does, if you don't want the moment about the point, then screw it and just do the second method. That was my understanding.
Because it's a determinant, which is nice though. So if you are going to do it method 1 though, in a calculator, you have to do 3 separate 2x2s, which is a pain. Versus you can do method 2 in a 3x3 determinant and just put it in a calculator and not have all these like 3 independent things that you have to go in and enter, which is a pain.
You don't need the IJK exactly. It's a big come up for finding that.
It's way faster on a calculator method 2.
Yeah.
Or on matrixcalc.org if you don't have a calculator.
Oh, now we're talking.
So the semantics of the steps, you could just read over the steps to understand that better. But the main point is that if you're trying to find a moment about a line, you're trying to find the component of that moment along the line. So you're doing a dot product. You're finding the component. In what we did, we found the component of the moment about point C along line CD. So we dotted it with the unit vector. Just like in forces, we use the dot product to find a component of a force in a certain line. We're doing the same thing. We're using the dot product to find the component of a moment along a certain line. Okay, what are some other questions you have? You're good? Everybody's good? Okay, so first we used right-hand rule on 2D problems last Tuesday. And then on Thursday, we looked at 2 and 3D problems and we solved for moments vectorially. And today we're finding moments about a line. On Thursday, we look at 3D problems and use right-hand rule. And that's when I think things will all gel together.
And then we get busy with a door hinge.
Yeah, soon. In a week. Oh, actually, no, he's doing the door hinge this weekend, this Friday. So he and I spoke this, I think that you guys are feeling that that Rob and I aren't communicating enough. So we're starting to make sure that we are. So this Sunday, we spent a lot of time talking about what's happening this week in his class as well as mine. So hopefully you'll feel better.
Great. Thank you for taking that time.
Yeah, well, we should have done it. I just, yeah, whatever. Okay, so you're going to take a quiz now. So right now it's 25 after 10 and the quiz starts at 10:30. And I'm going to share my screen to show you where it is. And I'm going to close these modules from last week. And our in-class quiz is a 2D problem. You're finding the moment due to using the right-hand rule, and you're finding the moment vectorially. And the reason that you're doing it both is so that you can check yourself. Again, in statics, there's tons of checks. You're going to find a moment about a point using the right-hand rule, and you're going to find the moment about the same point vectorially. In this way, you should get the same values. So some of you are ASC students, so then you take this quiz. You just get a little bit more time. I'm going to stop sharing for a moment. So if you want to get your cheat sheet together, we'll start it in 4 minutes.
$2D, right? The quiz is all 2D?
It's all 2D.
All right.
So here it is. It's under today's class, Tuesday, September 29th. And I could probably open it on my end too, if that's helpful. I don't know if that's helpful or not. Is that helpful or no?
Sure.
Is it helpful to have it open on my end or no? Not really. Probably doesn't matter because you could pull it open on yours. What do you want me to do?
Open it now. If you open it now, we get an extra 3 minutes.
Okay, sounds good. All right.
You don't have to do that, Joanne. We're going to wait until it's available, right?
I'm wondering if I could open it. Oh no, it looks like it's letting me open it. I wasn't sure if it was locked. Maybe I couldn't see it either. So the problem says you have a picture here on the right side. Uh-oh, this number looks like it's off. Let me check. I think it's 300.
I'm not sure you're sharing that other screen. You're sharing just the web browser.
Okay, so 2D problem, moment, right-hand rule, and vectors. This force here is 300. It looks like the last part of the circle of the 0 got it cut off, so it's 300. So using R cross F, solve for the moment about point A due to the 300 newtons. and then using the right-hand rule, solve for the moment about point A due to the 300 newtons. So it says 300 here anyway. So you're solving for the moment about point A using R cross F, and then solving for the moment about A doing right-hand rule, and you should get the same values. Then what is the moment about C due to the 300 Newton force? And what kind of motion is created by a moment? Okay, so you could get started.
Is the only distance given is the 750?
The only distance given is the 750, correct? And you have the 60 degrees and the 30 degrees.
Okay, thank you.